Dear students, today I would like to discuss an important concept in classical mechanics called equilibrium in potential fields. So, before solving the problems, I would like to give a short and clear introduction what is meant by equilibrium, different types of equilibriums, and their behavior under small disturbances. So, once we understand the basic idea, we will go through some carefully selected problems that connect theory with applications. So, this type of problems are not only important in exams, but also they give a basic building of the concept. So, a particle is said to be in equilibrium at a point x0 if the net force acting on it is 0. So, in potential theory, this type of points corresponds to very critical points of the potential energy function where system behaves uh, depends on the nature of the equilibrium, whether it remains at rest, it oscillates or diverges. So this concept is very vital in classical mechanics when we are dealing with difference of pendulums, spring masses, spring mass systems, and quantum mechanics, barrier stabilities, and thermodynamics, and different types of engineering problems. So as I said, the net force acting on the particle must be 0. That is f of x naught to the point f naught is 0. So we know uh, the relation between force and potential. That is F is equal to minus dV by dx. Okay, dx. So at this point, that is point x naught, this must be 0. So that is dV by dx at x naught is equal to 0. So this is the basic condition for to say a system is in equilibrium. So equilibrium occurs at stationary points where slope of the potential is 0. So the slope of the potential tells us where the system returns, escapes or stays in a new position. But the big question is what happens after a small displacement uh, given at x0. So this leads to classification of three different types of equilibrium. The first one is stable equilibrium. So a particle is said to be in stable equilibrium at point x0 if when a slightly displacement is given, it experiences a restoring force that pulls back to the original position x0. So for example, if you observe a particle at the center of the bowl, so given at represented by point P, if I give a small displacement, what happens? It will go to some extreme position and again come back to the rest position, and similar is the case in this side also. So the particle will move up and sideways positions and again come to the center position. Okay, so just like a simple pendulum given a force, so because of the restoring force it will come back to the rest position. Okay, so this type of equilibrium is called stable equilibrium. So mathematically, how can we represent a stable equilibrium? Is first of all we have to check dV by dx at x is equal to 0. So this is for to confirm equilibrium state. So this is to confirm equilibrium state only. So, but how to confirm it whether it is a stable equilibrium or not? So we have to go for we have to do a double derivation of that. So that is d square v by dx square at x naught. If this derivation yields a positive value, so then we can confirm that the particle is having stable equilibrium. Okay. So for example, if we consider a spring mass system described by Hooke's law, for example, a system like this. Okay. So the potential energy of this type of system is V is equal to half k x square. Okay. So the first derivative is dV by dx is equal to nothing but kx. So at x is equal to 0, automatically it will yield dv by dx is equal 0. Okay, that means the particle is having equilibrium point. So now what is the double derivative of this? So d square v by dx square will give k, a positive quantity, right? So we can say that, you can say a local minimum. So at x is equal 0, the spring is neither stretched nor compressed. If we displace it slightly, the restoring force F will pulls the mass into the initial position, leading to a oscillatory motion at point x is equal to 0. Okay, so this type of behavior is stable equilibrium. And what about the next one? That is unstable equilibrium. So a small displacement causes the particle to accelerate away from x naught. For example, if we observe this point P. So if we give any displacement, actually initially it is at rest on the peak of a inverted ball. Okay. Now if I give any minute displacement at this direction or this direction, it will go to an infinite new position and never come back to the original position P. So there is no tendency, not at all a tendency to come back to the mean position. So this type of behavior is unstable equilibrium. So mathematically, first of all, we have to check it for the condition of equilibrium, and after that, we have to check for the double derivation. That is dv by dx square at x naught. If it yields a negative value, so negative value, then we confirm that the system is at unstable equilibrium. For example, if a pencil balanced on the tip, the potential energy can be given as V of theta is equal to mg. For a pencil balanced on its tip, the potential is mgl into 1 minus cos theta. So where theta is the angle from the vertical, and m is the mass, g is acceleration due to gravity. Okay, and L is the length of the center of the mass. L is length of the center of the mass. Okay, so then in this case, what is first derivative? So dv by d theta. Here the variable is angle. So it will nothing but mg L sine theta. Right? So at theta is equal to 0. So what happens? This quantity will become 0. Okay, it will yield 0. So that means it represents equilibrium state. So then what about the double derivation? So d square v by d theta square, which will yield mgl cos theta. Yet theta is equal to 0. So what happens? So this will yield mgl. Obviously this is a positive quantity. So we can positive quantity. However, for a small angle theta, we need to behave at the top at theta is equal to pi. Theta is equal to pi. So at this position, so d square v by d theta square will yield a negative value, that is mgl, that is a to 0, indicating a local maximum. So physically, if we interpret this, at theta is equal to pi, the pencil is balanced upside down. So any small tilt causes it to permanently fail, as the potential energy decreases away from the equilibrium, making it is completely unstable. So this is how we can describe unstable equilibrium. So the next one is, the last important one is neutral equilibrium. So in this case, dv by dx is equal to 0, and also double derivation of potential, that is d square by dx square at x naught, is also 0. So this means the particle, the potential is flat in the vicinity of x naught, and the system neither returns nor escapes upon a small displacement. For example, this is the situation. So this is the original position. When we give a small displacement either this direction or this direction, so it will never return to the original position. Okay. So in such a systems, the potential is constant over a region. For example, V of x is called a constant potential, V is C. So then obviously dV by dx is equal to 0 and d square V by dx square is also 0. So the particle remains wherever it is placed. This is delicate balance without any curvature. So the important point is neutral equilibrium can be destroyed by tiny changes, making it less robust than stable equilibrium. So here is a potential energy curve. Potential position versus potential. So in this here we can see the all type of equilibrium. So this is the an x-axis position is given and y-axis potential energy is given. So this point represents, for example, A represents stable equilibrium, the point B represents unstable equilibrium, and C represents neutral equilibrium. So in these problems, first of all, we have to see. I'll write again. So while doing problems, first of all, we have to check whether dV by dx, okay, at x naught is equal to 0 or not to confirm equilibrium. Then the next step is we have to find d square by dx square at x naught. If it is a positive, we can say stable equilibrium. If it is negative, this is unstable equilibrium. And if it is 0, there is neutral equilibrium. Think based on this small introduction, let us do some important problems. So from easy to very difficult problem. So the first problem is a particle in a potential V of x is equal to x cube minus 3x has how many equilibria points and what are their types? So this is direct question. So first of all, what should we do? We have to check dV by dx is equal to 0. So from the given V of x is equal to 3x cube minus 3. So then dV by dx will yield, sorry, it's not 3x squared. V of x is equal to x cube minus 3x. So then dV by dx is equal to 3x square minus 3. Okay. So equating to 0 will yield x is equal to plus or minus 1. Plus or minus 1. So now we will see the behavior of the system at, so now we have 3 points, right? Plus 1 and minus 1. So now we have to see the behavior of the system at these 2 points. So for that, we first of all we have to find double derivation, that is d square v by dx square. Okay. So what is the value from the given function? It will be nothing but 6x. So at x is equal to plus 1, d square v by dx square will become 6. That is a positive quantity. So that means it represents a stable equilibrium position. Stable equilibrium position. Similarly, at x is equal to minus 1, just substitute these values. D square v by dx square is equal to minus 6. That is negative. So that means unstable equilibrium position. Unstable equilibrium. So for the given function, we have two positions, stable and unstable positions, given function. Okay. So now we'll see the next problem. So a particle of mass m moves in one dimension under a conservative force derived from a potential energy function given by V of x is equal 1 by 4 of x power 4 minus half into x square. So which of the following statement correctly identifies the nature of the equilibrium points of the system? So again, we will do the similar things. So initially, f of x is given, v of x. Square. So let us find dy by dx. So it will yield x cube minus x. Okay. So which can we write minus x into x square minus 1. So setting into 0, that is dx is equal to 0. So it will yield 3 points. So what are those? 0 plus 1 plus or minus 1. Okay. So now we have 3 points. So now we will see the behavior at each point. So for that, first of all, we have to find double derivation of the given potential. So what is that? Which will yield 3x square minus 1. So we have 3 cases, right? So at x is equal to 0, x is equal to 0, d square v by dx square is equal to, substituting 0 here, x square minus 1. So it will yield minus 1. So less than 0, that is the negative value representing unstable equilibrium. So similarly, at x is equal to plus 1. So that means d square v by dx square. So we can get d into 1 whole square minus 1. So 2, a positive value. So this is stable equilibrium. Okay. Even at x is equal to minus 1 also, we will get a positive value. D is equal to 0. This is a stable equilibrium. Okay. So the system has 2 stable equilibriums, 1 unstable equilibrium. Then we will go for. So in this problem, a particle of unit mass is moving along the x-axis under the influence of a potential energy function given by V of x is equal to x power 4 minus 4x square plus 3. Let x naught be an equilibrium point of the system. So which of the following statements is correct about the number and the nature of the equilibrium points? So there are 3 equilibrium points. That means 2 stable and 2 unstable. 2 stable and 1 unstable. In the B cases, there are 2 equilibrium points. Both are stable. And there is only 1 equilibrium point and it is unstable. There are 3 equilibrium points and all are unstable. So how to proceed? Simple. So given function is x power 4 minus 4x square plus 3. So initially find dy by dx and set it to 0. So that means, so we will get 4x into x square minus 2 is equal to 0. So upon solving it, so we will get x is equal to 0 or x is equal to plus or minus under root 2. So we have 3 points. We have to confirm what type of stability they will yield. Okay. So for that case, we have to find double derivation of the given potential function. So which will yield 12 x square minus 8. Okay. Now we substitute the 3 points. Example first one at x is equal to 0. So what happens to the double derivation? Just substitute x is equal to 0. So it will yield minus 8, right? So which is a negative quantity. So ultimately it is representing unstable equilibrium. Yet x is equal plus or minus root 2. So double derivation will yield, so 24 minus 8 nearly 16. So it is a positive value, represent stable equilibrium. So we have 3 points. 3 points here, one unstable, then two stable points. So that's it. So for example, from the given choices, we can say first choice represent this one. So the next one is a particle moves along x-axis under a conservative force derived from the potential energy function V of x is equal to 1 by 3 x cube minus alpha x square plus beta x, where alpha beta are the real constants. If the particle is in stable equilibrium at x is equal to, then what are the values of x and what are the values of alpha and beta? Okay, here directly they are mentioning that the particle is having possessing a stable equilibrium x is equal to. So now we need to find alpha and beta. Okay, so that is our condition. So V of x is equal to 1 by 3 x cube minus alpha x square plus beta x. Okay, so dv by dx will yield x square minus 2 alpha x plus beta. So it given that at x is equal to, it is having equilibrium. So that means if we substitute 2 at the given this equation 1, so we will get equilibrium position. So substitute 2 and equate to 0. Means dv by dx at x is equal to 2 is equal to 0. So we can get 2 square minus 2 alpha into 2 plus beta is equal to 0. So from this we can substitute. Finally we can get beta is equal to 4 alpha minus 4. Let us say this is equation 2. Okay. Actually we need to find both alpha and beta. Just we got a relation between them. This is not at all sufficient. So for that we go for second derivation. So what is second derivation? So d square v by dx square at x is equal to 2. Okay. So that means 2x minus 2 alpha. Okay. In the problem it is given that at x is equal to 2, the particle possesses stable equilibrium. So that is, what is the condition for stable equilibrium? D square by dx square at x is equal to 2 must be greater than 2. That means must be greater than to 0. This is a positive quantity. Alright, this is the important condition here. So that means at x is equal to 2, we will get 4 minus 2 alpha greater than 0. So which will yield alpha less than 2. Okay. So this is the condition. Now here we got two conditions. One is alpha less than 2 and another condition is beta is equal 4 alpha minus 4. Okay. From these conditions, we have to find alpha and beta. So how can we go for that? So in this type of problems, we can solve it from by observing the choices. Okay. So what is the first choice? First option, alpha is equal to 1 and beta is equal to 0. Alpha 1 and beta is equal to 0. Okay. So if you check the conditions, the first one is alpha must be less than 2. So it is valid here. Okay. So then we can proceed with the turn. So now we substitute. So we substitute alpha is equal to 1 in the second condition. So that means beta is equal to 4 into 1 minus 4, ultimately 0. So therefore alpha is equal to 1 and beta is equal to 0. So this is the first condition. I think we have to go for other options also. So what is the next option? The second option is alpha is equal to 2 and beta is equal to 4. Okay. So here the first condition is not valid. That means alpha must be less than 2. But here the condition is alpha is equal. So that means it is not at all a valid option. So then we go for next option. What is that? Alpha is equal to 1.5 and beta is equal to 2. Okay. So here alpha is less than 2. So then we can believe this option and we can check it. So if we say alpha is equal to 1.5, if we substitute in beta condition, b is equal to 4 into 1.5 minus 4. So ultimately it will yield 2. So this is also condition. So this is also valid. So now both A and C both are valid. Now we'll see the fourth condition. Fourth condition or D condition, that is alpha is equal to 3 and beta is equal to 8. So as our condition, alpha must be less than 2. But here alpha is 3. So straight away we can reject it. So from this problem, we can say both first option and third options are correct. Yes, I think this is very important problem. Here, a particle of mass m in the xy plane is subjected to a potential V of xy. So its Lagrangian is given by L is equal to 1 by 2 m into x dot square plus y dot square minus half into x square plus y square plus 2 into ln of modulus x minus y. So which of the following statement is correct corresponding to the equilibrium of the system? The first case is there are two there is no stable equilibrium at any finite value of xy. There is one stable equilibrium at the point xy is equal to 0 0 and two stable equilibrium at 1 1 and minus 1 minus 1. Two stable equilibrium at the points 1 minus 1 and minus 1 1. So this is very important. So we know that Lagrangian of a system is given by L is called T minus V. If you compare with the given problem, so what is the given problem? L is called m into x dot square plus y dot square minus half into x square plus y square plus 2 into ln of modulus of x minus y. Actually here we no need of any kinetic energy term. We separate the potential energy term only. So from this we can write potential energy is half into x square plus y square plus, sorry, ఇక్కడ minus 2 into ln of x minus y. Here the important term is the second one, ln of modulus of x minus y. So the modulus is important factor here. So because of absolute value, so we will have two type of cases. So what are those? X greater than y and x less than y. So this is only because of modulus. So we have to separately solve this for this both of these conditions. Okay. So first of all, we'll do case 1. So case 1, it is x greater than y. So in this case, potential, again writing potential, half into x square plus y square minus 2 into ln of x minus y. Okay. Now we compute the gradient, and also here we have to observe that the function is, well, the potential function is depending on x and y. So far we have seen potential is depending on one single variable, but here it is depending on both x and y. So we have to find gradient, that means dv by dx and dv by dy, both are needed. So dv by dx will yield x minus 2 by x minus y. So similarly dv by dy will yield y plus 2 by x minus y. So if you set both of them become to 0, that means let us say f is equal to 0, right? So if you set both of them to 0, it means x minus 2 by x minus y is equal to 0. So it will yield x into x minus y is equals to 2. So and the other one, y plus 2 by x minus y is equal to 0. Again we will get y into x minus y is equal to minus 2. Okay. Now if you observe here, we solve it, we have two equations. So these two equations are only possible when x is equal to 1 and y is equal to 1, y is equal to minus 1. So that means we have a equilibrium point at xy is equal to 1 comma minus 1. Okay. Now similarly we will go for the other case. So that means this one, case 2, it is x minus y. Similarly we will proceed. So here v is equal to half into x square plus y square minus 2 into ln of y minus x. Okay. So the gradient is dv by dx is equal to x plus 2 by y minus x. So similarly dv by dy is equal to y minus 2 by y minus x. So setting into 0, setting to zeros. Okay, and we solve it. X plus 2 by y minus x is equal to 0, and also y minus 2 by y minus x is equal to 0. Okay, so from this here you will get x into y minus x is equal to minus 2, and from here y into y minus x is equal to 2. So if you solve both of them, so you will get x is equal to minus 1 and y is equal to 1. So here also we will get to points x comma y is equal to minus 1 comma 1. So that means we have two equilibrium positions. So one is 1 comma minus 1, other one is minus 1 and 1. So we can confirm whether it is stable or unstable equilibrium. We have to find double derivation. That's it. I hope you enjoyed my lecture. Thank you.